Welcome back. Mr. Johnson with you once again. This is Lecture 18, Part 2, Periodic Trends, specifically ionization energy and electronegativity. But we are going to begin this conversation reviewing the trend in atomic size or atomic radius, which was what we left off with at the end of Lecture 18, Part 1. Just like to remind everybody that as you go down a group, there's no change in effective nuclear charge, but there's an increase in energy levels, and that makes atoms get bigger as we go down a group. So you go across a row, except for the D block, of course. There's no change in energy levels, but there's an increase in the effective nuclear charge, which pulls the electrons in successively closer to the nucleus, making the atom smaller. Again, the exception being across the D block, where as protons are gained, so are shielding electrons gained, which means there's no change in effective nuclear charge across the D block and no appreciable change in the size of the atoms. So we're going to flip our page to 327 of the ebook or 319 of our textbook to see a very characteristic graph, one that you're meant to be able to make sense of and interpret. Atomic number is is along the x-axis, atomic radius is on the y-axis. So as we march from left to right across the x-axis, we're proceeding through the periodic table. Here's hydrogen, a very small atom, just one proton, one energy level, and as you go from hydrogen to helium across row 1 or period 1, we see helium being smaller than hydrogen due to one more proton or an increase in effective nuclear charge. There's a big jump from helium to lithium as we go from period 1 to period 2. That second energy level makes lithium a significantly larger atom than helium. And then as you move across period 2, you see a noticeable drop in the size of the atoms as the effective nuclear charge increases across row 2 with no change in energy levels. Another big jump to sodium as you go to row 3 or period 3. A drop across period 3, big jump to potassium as you go to period 4, and then a drop across period 4, with the exception being in the D block here, where there isn't a significant change in the atomic size due to, again, no change in effective nuclear charge. And that pattern continues. You're, again, meant to be able to explain this or justify these trends based on what you just learned. You're also meant to be able to compare the sizes of ions, usually isoelectric ions. Ions that have a different number of protons but the same number of electrons. Ions that all have the same noble gas configuration. So we're looking at aluminum, fluoride, magnesium, nitride, sodium, neon, and oxide, these ions, and what their relative size would be based on what we just learned. So we're going to jump to the periodic table and look at what we think the trend would be in these ion sizes that all have the same electron configuration. So again, it's aluminum as an ion, magnesium, sodium, nitride, oxide, and fluoride, which all, when they become ions, assume neon's noble gas configuration, the nearest noble gas. What that means then is they all have 10 electrons. They all have 2 energy levels worth of electrons. So it's not going to be about the energy levels that affects their relative sizes, but rather their effective nuclear charge, or the number of protons. Because nitrogen has the fewest protons of all of these ions, but they all have the same number of energy levels, it will have the lowest effective nuclear charge, which means nitrogen will be the biggest. Aluminum, on the other hand, with the most protons and the highest effective nuclear charge, would be the smallest. So the trend in ion size from biggest to smallest would be nitrogen, followed by oxygen, followed by fluoride, because again, fewer protons means that the electrons will get sucked less far in or less close to the nucleus, followed by sodium, magnesium, and aluminum would be the smallest. So they're going to get successively smaller as we go through the periodic table. And that trend is depicted here in green on this page here in front of us. All right, we're finally on to ionization energy, the periodic trend that exists for ionization energy. The first thing we need to do is define what ionization energy is. Well, it is the energy, or the minimum energy required. It's an endothermic process required to move an electron from a gaseous atom, or if the atom is already an ion, to remove another electron. What the values, though, that we typically see in our book is based on a mole of atoms. So ionization energies are typically in kilojoules, the number of kilojoules of energy it takes per 1 mole of gaseous atoms to remove 1 electron from that atom. That's depicted here in this equation, where we can see the neutral gaseous atom having energy added to it, the ionization energy, resulting in that atom being an ion, a cation, a 1+ ion, and the loss or the emission of an electron. Enough energy can be added to an atom that its outside electron can be stripped or removed completely from that atom. The reason it's an endothermic process or an energy requiring process is that electrons are attracted to the nucleus due to the opposite charge between electrons and protons, and it always takes energy to overcome an attractive force. Ionization energy explains a lot about how atoms behave, which is what is written here in red and blue. It tells us how strongly an atom holds onto its outermost electrons. And this is a really important property because an element with a low ionization energy that doesn't hold on to its valence electrons very strongly will be more likely to lose those and form cations. And we're talking about metals. Metals on the left side of the periodic table form cations because they have relatively low ionization energies. A high ionization energy, on the other hand, might signal an element's tendency to gain electrons and as such form anions, negative ions. Or perhaps not at all, to share possibly, which we'll talk about later in electronegativity. So ionization energy can be used to predict how likely an atom is to gain versus lose electrons, among some other factors that it influences. What's really important to understand right now is that if the attractive force, think of that Coulomb's law, that simplified Coulomb's law we had. The force of attraction between a nucleus and the outermost electron is due to the effective nuclear charge over the number of energy levels. If the force of attraction between the nucleus and a valence electron is great, then it takes more energy. A greater force of attraction between the nucleus and a valence electron results in a greater ionization energy. Meanwhile, a lesser force of attraction, a lower force of attraction, would mean that less energy would be required to remove that electron that's more weakly attracted and would have a lower ionization energy. So if we can predict as we move through the periodic table what the force of attraction is, ionization energy follows that same trend. Again, a greater force of attraction results in higher ionization energies, and lower forces of attraction result in lower ionization energies. So we're looking at a periodic table, of course, again, and I've written a couple of things in red to remind you of as we contemplate the trend across a period for ionization energy and down a group or down a column. Again, the force of attraction that exists between the nucleus and a valence electron is equal to, in a simplistic form, the effective nuclear charge over the number of energy levels. And ionization energy is directly proportional to the force of attraction. A greater force of attraction results in a higher ionization energy. All right, so let's apply that. As we go across a period, we know that the number of energy levels doesn't change, but the effective nuclear charge goes up, so the force of attraction goes up. That means as we go across a period, the ionization energy also increases. Ionization energy increases across a period due to an increase in the effective nuclear charge or to the attractive force, an increase in the attractive force between the nucleus and one of the valence electrons, requiring more energy, therefore, for that electron to be removed. Again, ionization energy increases across a row. As we go down a column or down a group, we know the effective nuclear charge doesn't change, so the numerator doesn't change. The number of energy levels increases, which results in a weaker force of attraction and therefore a lower ionization energy. As we go down a column or down a group, ionization energy decreases due to an increased number of energy levels, resulting in a weaker force of attraction and therefore less energy being required to remove an outermost electron. Down a column, down a group, ionization energy decreases. And if we come back to our book, this is 329 of our ebook or 321 of our textbook, we can see in blue and in green those statements, which again is across a period, ionization energy increases, whereas down a group or down a column, ionization energy decreases. As we scroll up, we see another chart that is meant now to be understood or interpretable. It's quite common to be presented a chart like this and to be asked some specific questions about why we are seeing what we're seeing. So let's take a peek. Well, as we go from hydrogen to helium, as we go across the first row, there's a significant increase in ionization energy due to the doubling of the protons. A doubling of the effective nuclear charge essentially doubles the ionization energy. There's a huge drop from helium to lithium as we gain an entire additional energy level. The force of attraction is way lower. The effective nuclear charge is 1 now, not 2, and the distance is greater. Big drop as we go to the second row. And then as we go across the second row, we see a general increase in ionization energy as the effective nuclear charge increases. Big drop again as we go to the third row. Not only is the effective nuclear charge decreasing from neon to sodium, but there's an entire additional energy level. And there's a general increase across the third row, drop as we go to the fourth, general increase across the fourth, drop again. Now the question is, what are these little exceptions about? Why is there a drop from beryllium to boron and from nitrogen to oxygen? The same drop occurs from magnesium to aluminum and phosphorus to sulfur for a similar reason. That is going to be about electron configuration and orbital diagrams. So we're going to return to electron configuration and orbital diagrams to explain those exceptions or those strange drops. All right, let's explain the drop from beryllium to boron / from magnesium to aluminum first. When we go from beryllium to boron, you're going from the last term of beryllium's electron configuration of 2s2 to boron's being 2p1. Beryllium's last term is 2s2, beryllium's last term is 2p1. What that means is to remove one of beryllium's outermost electrons, it would be removed from the 2s sublevel, from the second energy level, but from the 2s. Boron's outermost electron, however, would be removed from the 2p. Even though it's in the same principal energy level, because it's in a slightly higher sublevel, it's actually a little bit further away from the nucleus and therefore easier to remove. So it's not as big a drop as we see going from one row all the way to the second row, but when you go from an s sublevel to a p sublevel, the electron is a little bit further away from the nucleus and takes less energy to remove, despite that the effective nuclear charge goes up. We see that going from 3s to 3p, and we'd see it from 4s to 4p as well. But the drop in ionization energy from nitrogen to oxygen and phosphorus to sulfur is a little bit trickier to explain, because nitrogen's outermost electron is in the 2p, and so is oxygen's. Phosphorus's outermost electron is in the 2p, and so is sulfur's. But if we look at nitrogen and oxygen's orbital diagrams side by side, we notice that nitrogen's outermost electrons in the 2p are each in their own orbital. They're quite well spaced out. They're in their own orbital. They are not exerting much repulsive force on any other electrons because they're in their own orbital. It's pretty stable to have a half-full sublevel, to have electrons in their own orbital spread out. Oxygen, though, compared to nitrogen, has 2 electrons in the same orbital that are in a relatively confined space together and are exerting quite a bit of repulsive force on each other. That repulsive force that they're exerting on each other makes it more likely that one of those electrons could be removed from the atom. Whenever you go from p3 to p4, from electrons that are all in their own orbital to the first time that they're paired up, even though there's an increase in effective nuclear charge, the electrons being paired up makes the electron a little bit easier to remove. So we see a slight drop from nitrogen to oxygen as we go from p3 to p4. When we go from unpaired electrons to the first time that they are paired, and we see the same thing as you go from 3p3 to 3p4 and from phosphorus to sulfur. So those are a couple of exceptions to be aware of. When you go from S to P, there's a slight drop, and from P3 to P4, there's a slight drop due to slightly different reasons. So far, what we've been talking about is what's called first ionization energy, the energy that it takes to remove the first valence electron from a neutral atom or from a mole of neutral atoms. But there's also second and third ionization energies, the energies it takes to remove an additional electron after the first was removed, or a third electron after the first 2 were removed. As our book says, we might expect that after removing 1 electron from an atom, further ionization energies increase, and they do. That occurs because each additional electron that's removed is being removed from an already increasingly positive ion. And that increasingly positive ion creates an even stronger hold on the remaining electrons. Furthermore, as more electrons leave the valence shell, there's less repulsive force that those electrons are exerting on each other, pushing the electrons away and making them easier to remove. So there's always an increase from the first to the second ionization energy and from the second to the third. But sometimes that increase is substantial. Notice in beryllium's case that the increase from the first ionization energy to the second is appreciable. It's a 2-fold increase. But from the second to the third, It's an 8-fold or a 9-fold increase. Why is there such a great difference between the first ionization energy and the second, and less a big difference between the second and the third, and less a big difference between the first and the second? Goes back to the periodic table and beryllium's electron configuration. So here's beryllium on the periodic table, which is in the second row, second column. And again, there's a big jump from the second to the third ionization energy for beryllium. Well, if we get rid of the first electron in beryllium, it's coming out of the 2s sublevel. We would take a 2s2 down to a 2s1. The second ionization energy, and we'd be at lithium right now, the second ionization energy accounts for the loss of this electron out of the second energy level also. So there's going to be a jump, but not a huge jump, because it's still out of the second energy level. So we would turn 2s1 into just 1s2. The third ionization energy, though, is removing now an electron from the first energy level, not the second anymore. And because the first energy level is so much closer to the nucleus than the second, and there's a way stronger attractive force, the ionization energy is significantly greater. As we go from the second energy level to the first, significant increase in ionization energy. We should be able to expect where this giant jump would be for any element. For aluminum, for example, the first ionization energy would be removing an electron from the third energy level. It would take us to magnesium. The second ionization energy would also be removed from the third energy level. It would take us to sodium. So there'll be an increase, but not a huge increase. The third ionization energy would also be removing an electron from the third energy level and would be taking that atom to neon. And then it's the fourth ionization energy for aluminum that would be a huge increase from the third, because now that fourth electron that's being removed is being removed from the fourth energy level. So I would recommend that you try this practice problem now on the next page, 331 of our ebook, and to pause the video and come back after you're done and compare your answer to mine. Again, try this practice problem here on page 331 of our ebook. So I've starred the elements that were in that first practice problem: cesium, rubidium, sodium, magnesium, aluminum, silicon, sulfur, chlorine, and argon. The first thing we should appreciate is that atoms that are higher up in the periodic table have fewer energy levels, and fewer energy levels results in a much stronger force of attraction. So these elements in the third row, or third period, will have a greater force of attraction than will rubidium and cesium, and will have a higher ionization energy. So we're ranking from the highest ionization energy to the lowest. We know that as we go across a period, the ionization energy increases. So argon, being the furthest right in the periodic table, is going to have the greatest ionization energy, followed by sulfur, followed by silicon, followed by aluminum, followed by magnesium, followed by sodium. And then with significantly lower ionization energies, being further down in the periodic table, we get to rubidium and cesium. Rubidium is above cesium, so with one fewer energy level and the same effective nuclear charge, rubidium will have a greater ionization energy than will cesium. So there is the ranking of ionization energies from greatest to least based on the pattern we just learned. Question 2, members of this chemical family that have the highest ionization energy in their period or in their row would be the noble gases, being further to the right and having a higher effective nuclear charge, stronger force of attraction, higher ionization energy, and the alkali metals being on the far left, or the group 1 metals, would have the lowest ionization energy in their period. In the family or in the group, the highest ionization energy are those that are in period 1. The further up in a group an element is, the higher the ionization energy, and the lowest down in a family or in a group would be the period 7 elements. Question 3. We talked about, hopefully you recollect that, even though boron has one more proton, has a higher effective nuclear charge, when its outermost electron is removed, it's removed from the 2p sublevel, which is slightly further away from the nucleus in the 2s, creating a weaker force of attraction and a slightly lower ionization energy, again, despite that it's to the right of beryllium and has one more proton. All right, we're on to our final trend, which is electronegativity, and we're on page 331 of our ebook, same page we're on for that practice problem. Electronegativity is defined as the relative ability, so these are values relative to each other, the relative ability of a bonded atom to attract a shared pair of electrons. Electronegativity is only relevant, it only arises when we are contemplating how attracted an atom is to electrons it's sharing with another atom. Again, how attracted an atom is to electrons that it's sharing with another atom is electronegativity. While that will have more relevance later, and while it will make more sense when we look at bonding later, for you right now, you can think of electronegativity as how attracted an atom is to its own valence electrons. Because how attracted an atom is to its own valence electrons correlates with how attracted it is to electrons it will be sharing with another atom. Except for noble gases. Because noble gases have a very strong attraction to their own electrons, they are the furthest to the right in their period, but because they don't bond, they will not be attracted to shared electrons because they don't share. So noble gases don't actually have electronegativity values because they don't share electrons. Again, electronegativity is how attracted an atom is to electrons that is sharing with another atom, but for you right now, it can mean how attracted an atom is to its own valence electrons. What this means then is that because the force of attraction that an atom has to its electrons is directly related to ionization energy, and we already know the trends or patterns for ionization energy, we can apply those same trends, those same patterns, and those same explanations to electronegativity. Ionization energy and electronegativity follow the same general patterns. One exception being, though, written here in blue, that noble gases do not have electronegativity values. And those exceptions we saw, those drops in ionization energy from S to P or from P3 to P4, do not arise for electronegativity. Once again, electronegativity can be thought of right now as how attracted an atom is to its own valence electrons. And that pattern follows the same pattern as ionization energy did, with a few exceptions. Much like we saw ionization energy increasing across the period or across the row, so too do we see that trend for electronegativity. And as ionization energy decreases down a column, so does electronegativity. So too can we say that as you go up a column or up a group, electronegativity increases. The general trend for electronegativity is that it increases as you go toward the upper right of the periodic table, toward where there are more protons, a higher effective nuclear charge, and or where there are fewer energy levels, creating that stronger force of attraction. These values that are embedded within the periodic table are electronegativity values. They're unitless, they're only relative to each other, and what we will use them for later is to find the difference between two atoms' electronegativities to know what type of bond they form. So as we look at the pattern here, we can see it being substantiated by what we already know to be true. Hydrogen has an electronegativity of 2.1. As you go down the group, the electronegativity values fall as the force of attraction between the nucleus and the valence electrons weakens due to increased numbers of energy levels. And as we go across a period or across a row, we see that trend as well showing up in these numbers. They are increasing due to no change in energy levels, but due to an increased effective nuclear charge, a greater force of attraction, and therefore a greater ionization energy. And then notice once again that the noble gases do not have electronegativity values, because although they are attracted to their own valence electrons, they won't share electrons with another atom, which is what electronegativity is really about. So here's another one of those graphs or charts with atomic number on the x-axis, and in this case electronegativity on the y-axis. And let's just look at this together to see how it makes sense. So we see a drop from hydrogen to lithium. We are skipping helium because helium doesn't have a value as you go down from row 1 to row 2. More energy levels, weaker force of attraction, lower electronegativity. There's a general linear march as you go across the second period to fluorine, which has the highest electronegativity in that period and on the periodic table. Drop to sodium, third period, increase across the third period, drop to sodium going to the, potassium going to the fourth period, and then a general increase as you go across the fourth with some weird things happening in the D block, which tends to happen for reasons right now we don't need to know. So we're going to leave off with this great little graphic here showing all of the trends that we've been talking about over these last couple of lectures. I'll begin with the middle part. We know that this zigzaggy line here differentiates metals from nonmetals. The further to the left or further to the lower left we are in the periodic table, the more metallic elements are. The further to the upper right, the more non-metallic they are. We know as we go down, atoms get bigger due to increased energy levels, no change in effective nuclear charge. And as we go right, they get smaller, or we could say to the left they get bigger due to a lesser effective nuclear charge, not pulling the electrons in as close, resulting in bigger atoms. Ionization energy and electronegativity follow the same pattern. They both increase as you go across, as the attractive force or the electron affinity increases due to an increase in effective nuclear charge. And they also both increase as you go up. We tended to be talking about down, but they increase as you go up due to fewer energy levels or a greater electron affinity / a greater force of attraction. Hopefully, this graphic makes you as happy as it does me, and I wish you well in whatever it is that comes your way the rest of this beautiful day. Take care, everybody. Look forward to seeing you in Lecture 19, or in the real world. I exist in the real world as well. You may not know that.